So while preprocessing runs, we can go over the last section of the configuration file, the evaluation. So the first item in the evaluation is the data set, which defines which of the splits you want to use, which of the splits you want to evaluate. So notice in this case we have test, but you can change this to training or validation. Next, we have the folds. So for the evaluation, you can actually define multiple folds and it will do them in one run. So if you just want one run to do all of them, then you just add more numbers to that square bracket. So 0, 1, 2, and so on. Now for the epochs, here you see best. Another option is last. So best simply means that we will grab the patient with the we will grab the weights for the model that resulted in the lowest or best validation error. If this said last, that would just mean that we grab the last weight. So if we train for 1,000 epochs, we will grab the 1,000th weight. So now batch size, this is a little different than the batch size. Well, different, but also the same. And I guess I'll elaborate. But before, the batch size was how many patients we combine to feed the model, and the model is updating and so on. Now, the models can take different batch sizes. They can be whatever, as long as your memory can handle it. Now, for evaluation, it is beneficial to actually feed the model batches of inputs for the same patient. Remember, we actually take a volume and we split it into patches. So instead of doing a single patch and performing inference for a single patch, we can actually give the model 16 patches and perform inference for 16 patches in one go. So then that allows us to get more of the outputs in one go, as opposed to just using a single patch, single prediction, and then accumulating them and so on. So this is actually for inference, and it's how many chunks of one patient you want to feed to your model, your trained model at a time, so that you can speed up inference. Increasing this makes inference faster, decreasing it makes it slower, but there is always a trade-off between speed and memory. Now, post-processing, this is steps after you grab your final, so after you generate your final answer, so to speak, you can do additional things like you can multiply the final volume by the body mass to clean any mispredictions or errors outside of the body where it doesn't matter. Another thing you can do is for the patches that you're generating, it is typical or is recommended that you actually either throw away the edges or you taper them. You multiply them by a function that has lower values at the end versus the middle. And to sketch that out, we go back to our notebook here. So if you have a patch, instead of just taking these patches and multiplying them, you actually taper the edges. How that looks if I do a profile, right? So the data will look something like this, right? So that's the tapering function will look something like that. The data looks however, but you're multiplying the actual data by numbers that are smaller at the edges versus the middle. And you do that for all the patches. So basically saying that the edges where the models are less accurate, a consequence of like convolutional operations actually, you're saying that those edges should have lower weight during the combination steps. And this actually allows you to avoid issues like very strong like edges where patches overlap and so on, like lines that show up if you do not apply things like this. So the different windowing types that you can use, Gaussian, hand. I think the one that I've had the most success with is actually a hand window. So that's what I would recommend. So this one over here. So I would recommend using that one. And then if we go back over here, the overlap fraction, this is for the patches, what fraction of the of one patch should be overlapped by another patch. The patches are all the same, so we're saying 50%. So there is like half and half. Then the metrics that we actually want to compute. So isodose DSC. So this is a metric that you can learn about by looking at my publication or the one from UT Southwestern, Nguyen. He uses this in several of his papers. Then other metrics like mean dose difference, mean absolute dose difference, and so on. You can all see them listed in there. Dose score and DVH score, that comes from the APM competition. So you can read the paper by Bavier, or there's some other papers as well, including mine, where I describe these functions. And then some other metrics that you can compute. So you can change this to have more or less. The code knows how to take these values and then use them to compute any D value that you want, any V value that you want. Now, low dose threshold, that means that for some of these metrics, you only want to look at those values that are above this percentage of the maximum of each patient. So in this case, we're not using values below 10% of the maximum. So that avoids inflating this mean dose and mean dose difference and so on by taking a lot of voxels where the errors are low and the dose was low to begin with. And something else. So in the optimization section, we also have other things that I didn't discuss, like prefetching. I wouldn't recommend changing this too much. So prefetching is just when the I guess execution itself, so your pipelines prepare data for the GPUs ahead of time, so that the GPU, once it finishes processing an input, has another input ready to go, and it doesn't have to wait for the CPU to process it. So if you do not do this, then you have CPU prepares data, GPU computes, and then lets the CPU know that it finished, and then CPU prepares data, then GPU computes. Now, by having prefetching, these things can happen, without asynchronously, or whatever the word is, and you can have the CPU preparing data ahead of time while the GPU is computing. So once the GPU is done, data is ready, and it can go ahead and boot and compute again. You can cache the validation set or the training set to avoid having to read that, since the validation set doesn't actually get augmented. It's good to actually cache it so that that data is in the RAM and has a much faster way of being used by the model, by the GPUs in this case. And number of parallel calls and prefetch buffer size. These numbers influence the parallelization level of your training pipeline. So TensorFlow can do a lot of the steps that it implements in parallel, and how many CPUs you want to use is defined here. So what I found that in Kubernetes, if I'm using H100s, I like to use 24 here, 24 here, and 20 here. That's what I usually do. What I usually use. XLA is an optimization technique that allows you to perform inference faster. You optimize your model with this scheme. You can read about it online. And mixed precision is a way to speed up training by using lower precision inputs when allowed.